Howdy, everybody. Hope everything's going well wherever, whenever you are. We're here for day 19. Day 19 actually wasn't too tough of a problem, I didn't think, especially if you're familiar with dynamic programming and memoization. So we'll just go over it really quick. And again, I have plans for doing revisits of some of these days. I found better problems. I think I've made a few mistakes. Um, anyway, I'll definitely do some revisits. So if you see things you'd like me to talk about during any of the problems or parts you didn't understand, just feel free to add those to the comments, and I'll make sure and include them in some revisit videos. So there you go, day 19. Let's talk about it a little bit. Excuse me. It's called linen layout, and essentially you're at a hotel. By the way, I really like that they've come back to some of these things. I actually remember some Gear Island stuff, right? So this was just last year, I think. And so anyway, it's kind of fun that they have like the flashbacks to some of these things or callbacks to some of these things because it's the 10-year anniversary. So anyway, you got a bunch of towels, and they're striped towels, and they can be any of these colors. And that there's some expert that has said, "Hey, here are the allowed design patterns, um, or maybe the best way to say it, segments of patterns that are allowed within a towel." And so then they're going to give you a bunch of towels, and your job for part one is to say, do they meet all the design segments? So what does that look like? So here's all the little design pieces that are allowed right here. So these are the different like color combinations that are allowed. And then here's all the towels. And essentially the question it's saying is, can you take this string? Can you make this string from uh, you know, one or more of these patterns in here combined, right? So you can imagine that this one you could say, oh, I can do BR right here, and then I can do WR right here, and then I can do R right here to get BRWRR. That's what it's asking you to do. So if you looked at this before, and in fact the way I just did it, you can kind of imagine in yourself the idea of, oh, I could kind of do this recursively, right? What if I just try and figure out, will can I figure out this, the first part of the towel, and see if I can find a pattern for that. And if I do, then I just have to figure out the rest. Can I solve the rest of them? Okay. Um, and that is called dynamic programming, which is right here. I have the Wikipedia. And the idea behind dynamic programming is, can you take a large problem and solve it in small little chunks? And if you can break it down into those simpler sub problems, you can then you know uh, solve each of those smaller problems to eventually come out to a bigger problem. And that's a very general term for when you call dynamic programming, because you'll actually realize that a lot of the problems we've solved in the past have actually used this, right? Um, Pathfinding algorithms, things like that are great, are kind of ways that fit under the dynamic programming thing. We tend though to like have say like, oh, graph problems fit in this category, and the dynamic programmings tend to be like, can you break down into little pieces? But if you're speaking like from a computer science dynamic programming, there's actually a broad structure that fits in there. For our case though, and for puzzle solving, when someone says dynamic programming, what they generally mean is, can you break it up into small problems and solve that, usually recursively, but you can also use other tools like tables and stuff like that. I'll stick with I solved this one recursively, so we'll probably just keep resolve. I'll talk about the recursive dynamic programming a lot, but I believe there's been other times when I maybe used a table, and the idea behind the table is you create like a solution of answer table that's maybe a 2D, or depending on the problem set, 3D or whatever. I think there's actually ones that could be a 1D set. But anyway, you could create a 2D table, and like you solve this small problem, and then you solve these two small problems, and then the solution to this problem right here is like the smallest of the two adjacent ones, and that's essentially how the table works. But we're just gonna do we're going to do recursive because it seemed to fit better for this day, right? Is where you say, oh, I can just find pieces that work, and keep doing that until I either find a solution or don't. Okay. So again, one of the things about dynamic programming is that it feels a little bit like magic. And I think I've said this before about other things, but the idea that is like, oh, if I just solve a small problem, subset of the problem, and then I do that over and over again, eventually I get to like a whole solution. That seems kind of magic. And so sometimes it takes a little bit of thinking, and I've heard that with recursion as well, because I don't know, sometimes the solution seems too simple, maybe is the way to think about it. Is like your mind starts wrapping around all the things that you need to do to solve this, and it feels complex, yet the solution is small and elegant. So if you and that can be feel kind of cool and empowering when you solve it, right? One thing I'll point out too is that it's very common to memoize your solution. And I think we've done that in a previous day. I went and looked, and there was a day where we did it, right? Where you like say, there's no reason for me to recompute something if I've already solved it before. And so that's a very common way, or sorry, a very common technique when you're doing dynamic programming, right? So just to like graph the idea out at like a really high level, let's take one of them and just try and solve it in a dynamic programming way. So we have these values here that we can pull from. U, RB, GB, and BR. And let's just do the first one, BRWRR. Okay, so we already know we can solve that one. But you can imagine just breaking it up. And we want to take kind of an iterative approach to this, right? And so we'll just say, oh, does R solve for the first part of this solution? No. How about WR? No. B? Oh, B does solve for it. So I then ask myself that I know that B solves for this part. So now I just ask the question, can I solve RWRR, right? And so I'm going to go through this, and it's like, oh, yes, I can. Right here, right? I can do this R right here. Did I do that right? Is it the right one? BRWRR. Yes, it is. I think I solved it another way before. So I can say, oh, I can solve for, can I pull an R out of there? Yes, I can. I can do it right here. So now I just have to solve for WRR, right? Does R do that? No. Does WR do that? Yes. So now I just need to solve for R, right? And of course, R fits there. So because this one works and this one works, then this one works. And now I know that the whole thing works. So the whole thing is yes. Okay. Let's find one that doesn't work so you can get an example. BBRGWB. So the next one is BBRWGB. Is that right? BBRRGWB. RGWB. Okay. So this one kind of starts off the same. I know I can trim off the B. So that's the first one I encounter. So I trim off the B, BRGWB. And I can trim off another B. I hit here. So now I'm asking myself, does RGWB work? And let's see, I can pull off an R. So I pull off the R. So now I have GWB. G, I can pull off a G. So now I ask myself, does WB work? There is no, that WR won't work. BWU, is that the, did I do that right? Yeah, BWU. Oh, this does not work, right? So this does not work. I can kind of roll up now and say, can I do something different? Does a GW no, RG no? Yeah, so up here I could technically go BR. I could pull BR off of here as opposed to just a B. So instead of pulling just a B, I pull a BR, and that gives me GWB. But I've already seen that GWB doesn't work, right? Because this one won't solve for it. So I already know that way doesn't work either if I pull off a GR. So you can think about the tree that I kind of went through was here to here to here, and here to here. And this is where memoization helps you, right? Is like, um, there's no reason for me to continue down this tree if I've already seen before that this one doesn't work, right? I know that GWB doesn't solve. So, in fact, I know that this doesn't solve now either, right? And so, there's no need when I'm trying another solution to keep going down that path because I've already seen GWB before. And that's where memoization helps, right? Is you're doing this kind of recursive, can I solve just a sub problem? And so like what is the sub problem? First, let's just start with that. What is the sub problem here? Is like can I find a valid prefix? And then repeat for rest, like the rest of the stuff, right? These are just the two sub problems that I'm trying to solve, right? And again, so if we go back to memoization, right? There's no reason for me to try and like solve this sub problem if I've seen it before. The idea being is like I'm creating like this graph for this one, right? So this is the whole problem, and maybe I can trim again, like I can trim off a B or a BB or maybe a BBR, right? Depending on the thing. And so you might say, oh, there's 3 different possible ways to go down here. And then over on this side, if I'm going like, oh, there's 2 possible ways here, and then this one has 3, and this one only has 1, and this one does work, this one doesn't, and this one doesn't, and this one doesn't. So like I found this solution, right? Well, I should say this one doesn't either. But if let's say like I go to this node now and I go like this and I break off, if this node is equal to this node, they have the same value, and I know this one was a no, then I know this one is a no as well, right? Does that make sense? Hopefully that helps you understand what memoization is. There's no need for me to like keep traversing like the decision tree. I have all these like different solutions that I'm checking, and if I've already seen one before, there's no need for me to check it again, if that makes sense. So that's the intuition behind solving this problem, right? I have a bunch of strings that I'm going to test, and I'm going to see can I match a prefix, and if I can, then I'm going to try and match the substring, and I'm just going to keep doing that until, at least for part 1, what part 1 is asking you is, can you find a solution? Like, is there any solution that is possible? And if there is, then it gets a point, right? You count it. So let's look at that in code. This is actually relatively short code, and it turns out you could actually do part 1 and part 2 together. I'll talk about that in a second, but let's just focus on part 1. What do I do? Oh, I have this up here from previously. I was trying to use some cached things, but kind of ran into some problems. Anyway, let's see here. So to parse the input, this one felt pretty simple because I could just do a split once, and then I could either split, and then the patterns are split by comma, which is this part right here, and then the problems are just split by lines, which is the rest of this part right here, right? So I just collect those 2 things. And then for part 1, once I have that like solve function, which I show you in a minute, all I have to do is iterate through each of these over here and call the solve solution finder for each of them and then count up the ones that were true, right? So I use filter to find the ones that are true and count them up, and that gives me my part 1. So what does it look like? Oh, I'm not using a memo here. That's kind of funny. I was dorking around with some stuff, and so that's why it's not here. If let some result memo dot insert we need to do one more right here. The memo isn't necessarily needed on part 1, but I thought I'd still show it to you here. That why isn't it needed on part 1 is because you're just trying to find a single solution, right? And so it's pretty easy for you to just make your way down and check. The inputs are pretty large. You can see the actual input. There's a lot of values, and then it's a relatively large string that you have to check through. But it's fast enough as you technically don't need to use memoization. I just do it because I wasn't sure, and so it's not hard to add memo. But the first thing you do when you're doing dynamic programming recursively, especially, I guess it applies to all of them, but what are the base cases, right? And so in our base cases, well, if the problem is an empty string, now I don't have to do anything, right? I know I'm done. And so the answer is true, right? An empty string means I've gone through the whole string and I've been able to like remove parts of the string until I've gotten to an empty string. So that returns true. If I've memoized it and seen it before, then I can also just return that result, right? I already know what the answer is. I've tested it before and no need to do it again. Otherwise, I'm going to loop through all the patterns and I'm going to say, hey, does my problem start with one of those, with that pattern? And if it does, then I'm going to try and solve the sub problem. And that's what this part is doing right here, right? Okay, let me solve the sub problem and see if I can figure out what that is. And if it's true, I memoize it, I save it, the results, and return true. Otherwise, I just keep trying problems or patterns until I've exhausted all the patterns. And if I don't find any, then I return false. And so this is all happening recursively, and eventually I'm getting to the, did I solve it or not, and it returns true or false. You'll notice here I'm using lifetimes in Rust if you're still kind of new to Rust. I think I needed to use lifetimes here. I'm pretty sure if I get rid of them, it doesn't work. And the reason is because I'm using this like hash map. And so the hash map needs to know that this string is going to be around as long as this function is. And so that's why you have to provide a lifetime here. Like if I get rid of it, I'm almost sure it will fail. We'll try it. Yes, it doesn't like this, right? It says, hey, I don't know how long these things are going to live. So you do have to like keep the lifetimes in here. So that's just a Rust thing, right? If you were using like C or whatever, you'd be managing your own pointers and references, so you wouldn't care. If you're using Python just is like magic. It figures it out for you, right? So you wouldn't have to worry about that. But because we're being very strict here with the Rust programming language, we need to say, hey, this string is going to last as long as, this function. And so it will still be there. So that's why you'd have to do that. But anyway, you can see the code is relatively small, but you're doing quite a powerful thing. And why is it powerful? Is because you're just breaking it into little chunks, right? You're breaking it into little chunks. So that's dynamic programming in part 1. Part 2 is no different. Well, it is different, but it's solved the same way. Part 2 just says, okay, that's very good, but some of the arrangements you've made, the designer doesn't like this style of. And so they want you to produce all of the different possible ways that you could solve the problem. And so they give you some examples here, like BRWRR could be built this way or this way, right? And then the designer can choose between these, right? This is where you definitely would have to use memoization, and the way to think about it, like what is the intuition behind it, is you're no longer just finding one case where it works. You now have to find all the cases where it works, and so you're almost doing like an n squared, right? Instead of doing like a maybe an n log n to search for one that works, you're now doing an n squared, right? And you can see there is a lot of patterns, and these are relatively large, so that n squared becomes really big. In fact, if you look, the solution is like 692 trillion, right? So that's not something you could just easily brute force on a program, on a computer. Although maybe lots of people have been into using GPUs and stuff like that. Maybe that's not a big problem if you have enough GPUs. I don't know. This doesn't really lend itself to GPU. But anyway, the point is, I bet you can make it work. So I don't want to say that no one will solve with GPU, because I've seen people do some cool stuff with it. What's changing though in part two is you're now saying this is really big, so I definitely want to memoize. I want to memoize this problem so that if I ever find a case that I've seen before, I don't have to do it again. And if you memoize it like outside of the solution set, outside of solving the problem, you can reuse it for all of the problems, right? So if there's patterns in part in like this first one that apply down here in some other ones, you can reuse those patterns, right? So notice like this one ends in WUW and this one ends in WUW. That's going to be very helpful because these ones have, it means that these ones can like leverage each other's knowledge, if that makes sense. Okay. So you and the difference now in part two is, again, you're not just saying does it work or doesn't it work, you're saying how many times does it work? And the answer might be 0, but the answer could be, millions or billions to get you up to 692 trillion, right? Especially with, I imagine some of these are really small, right? Yeah, some of them are like just 1 or 2 letters, and so it grows exponentially. So I'm just calling solve on part two. I'm also tracking the number of hits, and this is the number of like cache hits for my memo, because I thought that would be fun to show you how much the cache is actually used and how effective it is. So otherwise, the problem remains the same, except I'm going to get back a number now, and so I just want to sum up all those numbers to get my answer to part two. So here's part two. It actually doesn't look a lot different. I still have my base cases. In the case, though, here, when I reach the end, I can return a 1, meaning I found one solution. And then here's my memo. Here's where I'm counting my hits. So if I ever find one, I add a hit to it. And then otherwise, I'm looping. And instead of breaking or returning when I find a single solution, I'm just going to sum up all of the ways that I was able to solve this part of the problem, right? So I'm still going to go through all the patterns, and I'm going to see if my problem starts with that pattern. And if it does, I'm going to solve the sub pattern recursively and add that to my count. And then once I've gone through all of the cases, I can then memoize, right? And here is the answer down here, right? 692 million. And you can see my cache hit was 21,816. And what does that mean? Is like the idea is I have seen, I was able to like see some sub part of the problem that had already been solved. And so I don't have to go down and resolve it again. I can try and move this and show you, like, my guess is it will take forever to run. Yeah, we'll see how I'll let it run for a little while, but hopefully it gives you an idea of how powerful memoization is when you're solving these problems. And I tried to use the cached one here, but I ran into a lot of problems because why did I run into problems? I'm using these lifetimes right here, and I'm using these references. Obviously, that speeds it up, right? Because I don't have to like reallocate stuff. But cached doesn't like when I do that. Like if I add cached right here, it doesn't like me doing that because it wants to be able to copy and clone these copy or clone these values. And obviously, for each one, I don't want to recopy all of the patterns every single time. that actually slowed it down. I did get it to work for part two, but it was like extremely slow comparatively to this because of all the copies. So if you do get yours working and you can get it in a reasonably fast time, I definitely like to see it. But here we are. I've been running it for, I don't know, a minute or two now. Still haven't found the solution. It's never gonna, it's gonna take forever to finish, right? Because it's basically testing 692 trillion, uh, even more than that, ways to find it, right? Because there's a lot of them that will fail as well. But now when I do it with the memoization, it returns instantly. So keep that in mind. If you can break the problem into small pieces, dynamic programming is probably the way to solve it. And if you can memoize it, it's almost always going to improve the efficiency. And I'll say one last thing about today's solution. This is something that you can apply to real life programming. You know, a lot of people will say, "Oh, I'm never going to use Dijkstra's in my day-to-day work," and you might be right. The things that you're doing are probably, maybe they're not graph related, and so, or even if they are, you may not be asking yourself what's the shortest path type thing, right? But this is one that you can actually use: dynamic programming and memoization. I use this regularly, right? There's several places where I've gone and said, "Oh, this will solve it," and confounded my coworkers because it seems so simple. The solution seems so simple, but its ability to do it is like more effective than how they were trying to solve it before, right? So put this one in your pocket. If you don't know a lot about it, I'll try and remember to include the links for this, as well as I think maybe, I don't know if I'll find some videos, but there's definitely a lot of videos and books that talk about dynamic programming, and they're super helpful. The Wikipedia entry, the first part of it may feel a little crazy if you're not into math, but the computer science part of it is really helpful, right? It talks to you about the two different approaches: memoization, which you can go to, um, and things like that. Anyway, keep those in mind. I think keep this in mind. It'll be a great way to solve it. So, and other problems you run into. So with that, let's just look at some of these problems and see where we get. Me reading the input be like, okay, a Murloc. Yeah, there you go. They they do look really funny. That's a WoW reference for people, World of Warcraft reference for people who don't know. 10 more years, Eric. Yeah, I have a lot of fun with it, so I support them too. Uh, I have lots of fun doing these puzzles, and I'm sure even a few dollars goes a long way for them. So, yeah, feel free to support them. You Dagger Dragon when someone uses the wrong tag. Oh, I guess we have seen a couple places where we get flared for tag. I don't think they're banning anyone. They just say, "Hey, remember, uh, always translate into Welsh." Oh no. It thinks this might be Welsh. I'm using Firefox and I don't have the translator on, but it doesn't seem to think it in the Firefox one, but that's funny. It thought it was Welsh. Okay. I want to get everything out of the 20 cores. I don't know. I had 692 trillions a lot. I think what you'd have to do is refactor it so that instead of doing letters, you're doing like bytes or sorry, bits, and then you do the bit, you try and do the bit finding, and then you could do it on a GPU. I actually don't know. That might be a fun way. Rearrange the towels until the staff is satisfied. Give the staff more than 600 trillion possible combinations at once. Yeah, there you go. Some of them do. A lot of the problems don't make sense in real life, but a way to address. Here's 6 trillion options. What language is this input? Is this Welsh? That's hilarious. That it thinks it's Welsh. That's really funny. Okay. Oh, we got a stack trace. But yeah, you can see. Oh, yeah. Okay. So this is definitely leading to like a recursive thing. Why is that? Is because you can see it's like it's slowly growing here. The idea being that like he's trying to solve part of it. Regex, interesting. Could you actually solve this with regex? I guess this would work, right? You would want the plus here, right? But yeah, this is crazy. You just mash them together, you OR them together, and say, "Can you find this?" I mean, you are doing the brute force. NMK squared time. Yeah, I think you're doing much better. Doing doing it my way. Well, not my way, but the recursive dynamic programming way. If you add these at the beginning and the end, yeah. So he uses a plus. Here's his. It's not zoomed in. Sorry. Uh, yeah. You do a join of them, and then you do this. It's simple and it works because it leverages the regex standard library. Yeah, so that way would definitely work for regex part 1. I don't know how you do that in part 2 because the regex again is just giving you a yes or no. I would have to think about how the regex engine is going to give you the answer for part 2 because it normally only tells you like here's how many I found, not if a normal regex would just say did I find this pattern, but maybe you can ask for the number of ways to get it. Very cool. Let's see. Caching. Boom. Yeah, you'd be surprised at how much caching can do with solving problem spaces like this. And that's the part of like I mean, he says brute force here, but like I guess Mimo dynamic programming can kind of be thought as brute forcing. You're just brute forcing segments at a time. That makes sense. I don't know that I'd call it brute force, but like the meme this year has become brute force. And it's one of those, I don't think you're using that word the what way it's supposed to be used type thing. What? Counting yourself memorize, count a bazillion combinations. Okay. Yeah, Memoize solves it. Real brute forces people who gave up brute force because they thought it would take days. Oh, this is day 17. There's only one guy that can save us. That is crazy that these elves have gotten to know us so well and they're all like, here's how we do it. Oh, okay. So this is showing you the cache, and it looks like a Christmas tree, doesn't it? Right. Remember, like as you're caching, it actually tracks all of the solutions, and so it, you get you get a whole bunch. The cache is probably quite large, but that's what you want, right? Oh, here's a visualization. Oh, they turned it into what are these called? Segment trees or something? Very cool. Notice too how there's like duplicates, right? And so like you can solve it many different ways. That's where like memoization can help. Um, like if you know you can solve one this way or whatever. Bool any, int sum. Oh, is this like a Haskell thing? Yeah, you could just switch it from any bool any to int sum in Haskell. Haskell. I'd really like to get back to Haskell. It was kind of fun. Hash map cache. Boom, got it. Yeah, memoization was huge here, right? Uh Help me arrange these tiles and get free entry. Okay. Is it the calm before the storm? Yeah, there's definitely, it's possible that there will be much harder days because I don't know. Day 25 tends to be uh I guess the last few years that I remember solving it is like it's hard in that you have to like find an algorithm or know an algorithm or do some research on one, but there's usually only one part to day 25, and so it actually turns out not to be too hard to solve. But there can definitely be some really hard days. uh, okay, we'll look at a couple solutions and then we'll finish it up here because I don't think today was particularly difficult. I don't think I put there this year, but since some people had posted about having some trouble doing it with a try, and those who didn't post times, and my times are not too shabby. Okay, a try would work. Like, what is a try? It's like just a search graph tree. So you turn uh your patterns into a try. I can let's see if I can find it. It's like a prefix tree type thing. Yeah. Digital tree or prefix tree. The idea is you can like build your tree and it will say uh like it's really easy to find all the different ways that you can do things. And so how does this help you with the problem? Um that's a good question. How does it help you? Because you have like what you do is you'd put all of your patterns in here and then you just ask yourself like does the first part of the prefix solve the try? Let's go see what he does. Satisfying set. Try. Yeah, I mean he's doing the same thing recursively. He's just using a try to do the search. So like what they have changed is I'm using starts with and they're just using a try for it. Interesting. Like that maybe makes it faster. Mm, I mean, he's definitely in the microseconds, right? Okay, I mean that's interesting. You can definitely optimize these, and so this is cool. Usually, what the try is for, at least the way that I've used them, I think we maybe use them once in a day. But the idea is, can you find an efficient way to say like yes or no to anything, right? To these things, and a try works pretty well. Oh, it wasn't a try; it was something else that tells you yes for sure or no probably, but that was okay for the problem. I can't remember what it was. Anyway, it was not a try, but uh okay, that's an interesting way to solve the first part, and maybe it does speed it up. So, I think we've done this before where we said how fast can you make your code? And this one would be a fun one to try it on because I definitely think you could do some optimizations. Yeah, the try search is a good one. Uh Does he use a library? Oh, apparently there's a Rust library that does it. It'd be interesting to see how much faster it makes it, though. So, okay, very cool, very cool. Let's see here. Went for a memovized prefix search at first, was in the 25 millisecond range, but then realized I can shove all patterns in a set and check chunks on the input against the set. Without further ado, here's the heavy lifting. Runtime about 1 millisecond. I mean, I get it's different from CPU to CPU. So mine is 15 milliseconds. Like, do I get farther down by doing the hash set? So the patterns are now a hash set, and I just say for the first n characters, whatever the largest value of a pattern is, like for 0 to n, is it in there? And if it is, then I drop it in here. That wouldn't be too hard to test and see how much it speeds it up. Should we try it? I mean, let me just make sure that that's all he's doing. Max expect patterns contains if tally start for start size toweling. Oh, he actually tries them all. Oh, he's not. It's like recursion, right? Is like he's not really doing it recursively, but it's still a dynamic programming thing. He's just saying like, can I pull off some part of it? And if I do pull that off, and keep trying until I get to the end. Otherwise, try another size. Like I'm gonna try all the ones, the zeros ones. Interesting. Yeah, so he is also kind of using a table right here to like keep track of the counts and then incrementing the counts for each of them. Very cool. That's a cool way to do it. That's crazy that that solves in 1 millisecond. Hmm. That's really cool. DFS. Yeah, DFS is a good one. I mean, essentially, what we're doing is DFS. With our recursion. So I tried new for part 2, non-recursive DFS, where my stack contains an object of string and times observed. Yeah. So the thing is like any recursive function can be turned into a non-recursive function just by and the way you can think about it is, oh, I can just track the stack myself. And so the question is can you do that more efficiently than the CPU or the compiler? And sometimes the answer is yes, sometimes the answer is no. And so you just uh uh sometimes it's makes more sense to do it that way, especially if your stack is going to be deep, right? So the reason why you always see people using like Dijkstra or sometimes just doing a BFS manually or DFS manually without recursion is because they're like, oh, the depth may be very large. I don't know if that's the case here. Like these strings are relatively small. So even if you like imagine going like trying each of these strings, none of them are more than like 100 characters. So your recursive depth's never going to be like more than 100 or whatever. I don't know if that's the case, but like most Go, these are relatively small, so you don't need to worry about that. But in like a graph finding algorithm, you might, because you might say, oh, well, I may go hundreds or thousands deep, in which case the recursion's not good, right? And so you become the stack tracker, and that's where I use like the frontier a lot, or some people call it a stack or a queue, depending on whether they're doing a DFS or BFS. So interesting. That's a good way. That's yeah. We look at this code. Let's see what he does. It's in Golang. I don't know if I've said this before, but I actually use Golang daily at work. It's funny because I actually use quite a few languages between all the stuff. I really like Rust because I think it's got some cool ideas, but I love Go as well. We do a lot of stuff in JavaScript and TypeScript. And so while I'm in Go, sometimes I'll say like let variable equal, and I'll be like, nope, wrong language. You gotta have to kind of switch your language. Yeah, he's just doing a queue. And you can see like here's where he pops. You could potentially use, I think Go has a heap, doesn't it? Let me look. Yeah. I mean, because you're just using a stack, it's essentially a stack or a queue, right? And so it's pretty easy just to pop and push. Okay, very cool. Yeah, but he's just like kind of testing him. Okay. These are all very cool. I think these are all very interesting solutions. Again, I don't think this day was particularly crazy, so coming up with something new is kind of interesting. Oh, this one ran in 400 milliseconds. Is that just Python being Python? Find path, lists, pattern, DP, dict string, and pattern and DP return. Yeah, he calls a lot of times it's called memo. Python actually has, what is it called? Func Tools Cache. It's this thing right here. And you can do your own DP, or you can use theirs, and then you don't have to write your own code to do it. Much like the cached, I just couldn't get it to work with this one. So yeah, but it's just recursive and total. This function looks exactly like mine. The fact that it takes a half a second as opposed to mine taking tens of milliseconds is probably just that Python versus Rust. And then maybe he uses the func tools and it works faster. But yeah, this is my solution in Python essentially. Very cool, very cool. I think these are all great. I should be better about like thumbs upping these if we review them because I think they're all pretty cool. Where was that other one? This one right here. And these are great ways. I don't know. Maybe I can go back to them later and say, hey, here's how I do it faster or whatever. So there you go. Day 19 in the bag. Hopefully you got yours solved too. If not, keep at it. And I'd love to see it once you do it. It would be really awesome just to see what you got. So we'll be back tomorrow for day 20. Talk to you.